Today we're going to look at 3 different proofs for this limit right here. So the limit is limit as x goes to a of x to the n is equal to a to the n. That's our claim. We want to prove it, and here are 3 ways to do that. On the side here I have, it takes a lot of board space, on the side here I have a list of facts, I'll say. And for each of these proofs, before I do it, I'm going to mark down the facts that we're going to need. Why? So it gives you guys a sense of how elementary the proof is. Elementary basically means that you don't require a lot of knowledge beforehand. It doesn't mean easy if you're thinking elementary school. It means no prerequisites or few prerequisites compared to something less elementary. You'll see what I mean. So here's the first way that we're going to prove it, and I call it limit properties. You might guess it's going to use some properties of limits. So here are the ones we're going to use. We're going to use the product rule for limits, which says the limit of a product can be rewritten as the product of the limits, as long as those limits exist, of course. And the other property we use for proof number 1, it's this one at the bottom, limit as x goes to a of x is equal to a. I'm not going to prove any of these, but we are going to use these facts. So number 1, let's get started. This is what we want to show. Let's start with the left-hand side. Okay, what to do now? Well, exponentiation is just repeated multiplication, so let's do that. And maybe we get somewhere. So this is x times x a bunch of times, exactly n times. And this is very nice because now we can take advantage of the product rule. So using the product rule, we can rewrite this as the limit as x goes to a of x times the limit as x goes to a of x times the limit as x goes to a of x, and so on n times. N times. Just like that. Okay, this is really nice because we know how to evaluate every single one of these factors. And this is where the 4th fact here comes in. Limit as x goes to a of x is equal to a. So this is going to be a times a, so on n times. N times. And at the end, what's that? That's just a to the n, isn't it? So you can see way number 1, very clean. Not super elementary, we use those 2 properties. But there we go. We've shown this limit's true. If you wanted to do it from scratch though, you're going to be in for quite a bit of trouble because you need to prove the product rule and you need to prove this limit using epsilon delta, of course. And then you can finally show that this limit's true. Alright. Great. Let's move on to proof number 2. So here's where what I was saying makes a bit more sense when I was talking about things being elementary and less elementary, but not necessarily being easier or harder. So proof number 2. I'm gonna call it epsilon delta, sort of from scratch. Not really, but almost. Alright, so we're given the epsilon delta definition of the limit. We want to show that this limit is true. How are we going to do that? Well, what do we want? We want absolute value of x to the n minus a to the n to be less than epsilon when absolute value x minus a is less than delta, something like that. And the idea is, if we have this, we can control the size of x minus a. We can control how far x is from a. So if you've done epsilon delta proofs before, this first step, it's going to seem very familiar to you. The first step is to work backward. So you can think of this as our rough work. If we were actually proving something, we wouldn't really need the backward step. but the backward step really builds the motivation, because if I just said delta is equal to this algebraic mess, you'd say, how'd you get that answer? How'd you get that number? So we're going to work backward. That is starting with the delta part. So important to note, this part isn't logically correct. You can't do the backward part and then say, okay, I'm done. You need to do the forward part afterward. It's just a rough work. So if you're familiar with epsilon delta proofs for limits, especially for polynomials, you'll remember that when we see something like this, if we saw x squared minus a squared, we'd probably factor it into x minus a times x plus a. And that's nice because it produces an x minus a. So why don't we do the same thing here? This is nothing more than absolute value of x minus a. That's right, you can factor a difference of nth powers. Oh, this part here is kind of long, but it's really just x to the n plus 1 plus a x to the, x to the n minus 1 times a x to the n minus 2, so on until you get to x to the n minus 1. So if you know how to factor a cube, a difference of cubes, this is just an extension of that, and it is true for nth powers in general. Okay, what to do now? I like this part because I picked delta. I can directly control x minus a. This is a little harder to work with though. It'd be really nice if I could find an upper bound for this. Like if this was less than 5, I can guarantee this is less than 5, then I can choose delta to be epsilon over 5, and very nicely this thing will be less than epsilon. Okay, here's what I'm going to do. I have absolute value x minus a. What I'm going to do is I'm going to use the triangle inequality. So now I have absolute value of x to the n minus 1 plus absolute value a, absolute value x to the n minus 2, and so on to the absolute value of a to the n minus 1, like that. Okay, why did I do that? Here's what this should be a less than or equal to. Keep that in mind. This is very cool. This next step's going to be super unintuitive, and it's going to take you a second to realize what I just did. But here we go. This is going to be less than or equal to, ready for it? Absolute value of x plus absolute value of a to the n minus 1. Where'd that come from? So here's the idea. If we look back at the last line, well, notice the powers of the x descend and the powers of the a ascend. That reminds me a lot of the binomial theorem. The only difference is the binomial theorem would have coefficients here. You know, like the row of Pascal's triangle that corresponds to n minus 1. So, I don't know, maybe that was 3 and so on in the middle. So the idea is, what we actually have, that's less than the expansion of some binomial. Namely, it's less than the expansion of this binomial. Notice if we expand this, we get the same thing, except the terms in the middle have a coefficient that's greater than 1. So this part's valid. You can expand this if you want, and you'll see, indeed, this inequality is true. Okay, what to do now? Well, remember, we really like x minus a. So what I'm going to do is I'm going to force an x minus a from this absolute value of x. So how am I going to do that? Absolute value of x is nothing more than absolute value of x minus a plus a, which is less than or equal to absolute value of x minus a plus absolute value of a. So that's the idea. We're going to force an x minus a because I know how to control an x minus a. I control it by picking my delta. That's the only thing I have control over. So it's really nice if I have one of those. Alright, here we go. On our next line here we can write this is less than or equal to absolute value of x minus a. And then here we have absolute value of x minus a plus absolute value of a, and then plus the absolute value of a we had before. All to the power of n minus 1. Okay, pretty good. What we can do now is simplify things a little bit, and we can finally start guessing at what our delta should be. Very educated guess, but still technically a guess. Remember, we're working backward. Here's what we're going to do. This is equal to absolute value of x minus a, and then this is absolute value of x minus a plus 2 absolute value of a to the power of n minus 1. Remember, we can control delta. We can control x minus a. That's why we forced it earlier. So what I'm going to do is, I'm going to say I can make x minus a less than or equal to 1. And I can also make it less than or equal to, let's say less than or equal to epsilon over 1 plus 2 absolute value of a, all raised to the power of n minus 1. And the reason I do that is, you'll see in the next step, this is going to be very nice. In the next step, this is nothing more than less than or equal to epsilon over 1 plus 2 absolute value of a to the n minus 1 times, and remember, x minus a is less than or equal to 1, because I could pick delta to be 1, for example, or 0.5, times 1 plus 2 absolute value of a to the power of n minus 1, and look at that, it cancels out, and we get exactly epsilon. So, it looks like we're onto something. So here's what I'm going to do. Let's look back at everything we did. These are the only conditions we set on x minus a to make everything fall into place. So that's going to be used for our choice of delta. Namely, it'd be really nice if delta is nothing more than the minimum of 1 and epsilon over 1 plus absolute value of a to the power of n minus 1. And now we work backward. We have to go forward now to show this for real. So this was our rough work. Here we go. All right. So that's our choice of delta. Now we want to show that absolute value of x to the n minus a to the n is indeed less than epsilon. And it's going to look very similar to what we did at the end. So we have absolute value of x to the n minus a to the n. Okay. Well, we can factor it. Something like that. N minus 2. Deja vu. This is going to be less than or equal to absolute value of x minus a times absolute value of x plus absolute value of a all to the power of n minus 1. And this is going to be less than or equal to absolute value of x minus a, absolute value of x minus a again. Remember, we really like that because we can control it. Plus absolute value of a plus absolute value of a. And I'll just rewrite that as 2 times absolute value of a for brevity. Okay, now we can use our choice of delta to advantage. Remember why we force x minus a? It's the one thing we can control when we do epsilon delta. All we can control is the size of x minus a. So, with our choice of delta here, what do I know? I know at the very least, x minus a must be less than that thing, epsilon over 1 plus absolute value of a to the n minus 1. So, that's what we have. Sorry, that should be 2 absolute value of a to the n minus 1. And we also know that x minus a has to be less than or equal to 1. Alright. So, in other words, what did we just show? We showed that x to the n minus a to the n is, well, less than or equal to epsilon. as long as we choose this to be our delta. And we're done, aren't we? The challenger's given us a delta, and we're able to find an epsilon to make it work. So this is from scratch, epsilon delta. It uses none of our prerequisites here, none of our facts. So it's more elementary than proof number 1, but it's really not easier. It's actually a lot of work, isn't it? So there we go. Proof number 2, classic epsilon delta. A lot of work. But, I mean, it's elementary, isn't it? So the board has changed a little bit since we were last here. There's a lot more writing on it, as you might notice. This is proof number 3. It's titled Strong Induction. As you might guess, it uses mathematical induction, and it specifically uses strong induction. Very cool. Already looks really different from the other 2 that we did. Okay, so here are the facts we're going to use. There are more than I originally had, because it turns out you need a lot more, and I forgot a few of them. So we're going to use the constant rule for limits. We're going to use the, I'm not sure what you'd call that rule, but the limit as x goes to a of x is equal to a. We're going to use the scalar multiple rule. We're going to use the sum rule. We're going to use the product rule for limits. We're going to use this rule, or this fact, that differentiability implies continuity. Or stated otherwise, if f prime at a is defined, if the derivative is defined at a, then in fact the limit as x goes to a of f of x is equal to f of a. In other words, you can actually substitute the value you're approaching into the function, and that is the limiting value as well, by definition of continuity. And of course, we're going to use this fact, strong induction. It's just another thing that you need to know to understand this proof. So, very unelementary. Here's how we're going to start. We want to show that this is true. Well, how does induction work again? We want to show it's true for a base case. So our base case is going to be n equals 1. For n equals 1, our proposition becomes nothing more than the limit as x goes to a of x to the 1 equals a to the 1. So if we want to show it's true for the base case, what do we have to do? Absolutely nothing at all, because this is one of the facts that we have. This is one of the prerequisites for this proof. Good to go. Base case is true. For strong induction, for induction in general, you have this step, the induction hypothesis. So this is the part where we assume that our proposition is true. So assume true for n equals 1 to all the way up to k. So that's the induction hypothesis. And once we set this, the goal is to show that it must also be true for k plus 1 using this assumption. So we want to show true for k plus 1. Namely, we want to show that the limit as x goes to a of x to the k plus 1 is equal to a to the k plus 1, given that the proposition is also true for 1, 2, all the way up to k. So this is how strong induction differs from regular induction. In regular induction, you assume that it's just true for n equals k, the value just before. In strong induction, you assume it's true for all the values before. Okay, so here we go. How to do this? We're going to do it a really unintuitive way. We're going to do it using this property, differentiability implies continuity. If we can show x to the k is differentiable, then we've shown that this limit's true, because we can plug it in, because it's continuous, because it's differentiable. So it'd be good enough to show that x to the k plus 1 is differentiable. We're just going to use the definition of the limit. So the limit as x goes to a of the difference quotient, which looks like that, x minus a. if we can show that this is indeed a number, as in the limit exists at a, well then we're good to go because it's continuous and this fact is obviously true. What we're going to do, and this is reminiscent of the last epsilon delta proof number 2, limit as x goes to a, we're going to factor the numerator. And if we factor the numerator, what do we get? We get x minus a, and we have x to the k plus a x to the k minus 1, so on, all the way down to a to the k. Just like that, and in the denominator we have x minus a. Very cool. Okay, what now? That's very nice, isn't it? X minus a in the numerator, x minus a in the denominator, they cancel out, and we have nothing more than the limit as x goes to a of that factor, x to the k plus a x to the k minus 1 plus so on until the last term, a to the k. Okay, here's a hint. Whenever you do induction, you always want to take advantage of your induction hypothesis, because that's the thing that makes induction work at all. So if you're not using the induction hypothesis in your want to show step, you're probably not on the right track. So we're going to use that to guide us. It'd be really nice if we could take advantage of that. And here's how we're going to do it. By using the sum rule and the scalar multiple rule, as well as the constant rule eventually, but we'll get there. So by linearity of the limit, we can split this up and rewrite it as limit as x goes to a of x to the k plus a times the limit as x goes to a of x to the k minus 1, and then plus the values in the middle. The point is we're always pulling away the a and we're leaving the x inside the limit. The last term here becomes nothing more than a to the k limit as x goes to a of 1. Looks good, right? What now? Now we can use the induction hypothesis. So for each of these, right away we can see that that's going to be a to the k, and that's going to be a times a to the k minus 1, because the proposition is true for k minus 1, and so on in the middle. We can evaluate every single one of these limits, and the last one's just going to be 1. I'm going to tell you right away, yeah, you can do that. And it doesn't even matter what the numbers were exactly. All that matters is the limit exists. Because if the limit exists, what did we just show? That it's differentiable at the point A. And if it's differentiable at the point A, then this limit's true. So what have we shown? We've shown that x to the k plus 1 is differentiable. And finally, using fact number 2, fact number 3 here, differentiability implies continuity, we know that this is true. So we have that the limit as x goes to a of x to the k plus 1 is equal to a to the k plus 1. Look, we're done this step of strong induction. We're done the step where we show things are true using the induction hypothesis, because that's what we wanted to show, isn't it? So I'm going to put a big check mark here. And the conclusion, of course, because it's true for a base case, and because whenever it's true for n equals 1, 2, up to k, it's also true for k plus 1, then it must be true for all natural numbers n. So we're done. Wow, what an amazing last proof there. It combines all these cool things. It has strong induction. It uses all these facts. It's not elementary at all, but it is very elegant of a solution, isn't it? I hope you enjoyed this video. Thank you for watching.